Hello, everyone. My name is Precious Etiosa. I'm a first year PhD student in material science and engineering, and I'm working with Professor Shuboyejo. Basically, my research areas include biomedical and multifunctional engineering. And today, my presentation is going to be on XRD for medium and high entropy alloys. The outline for my presentation is as follows: a short historical review of medium and high entropy alloys, then a definition and properties of these alloys. Then we'll have a brief overview of what XRD is, as well as its applications in medium and high entropy alloys. And finally, we'll conclude. Um, Medium and high entropy alloys are barely 20 years old, though they are based on conventional alloy design, which are over 3,000 years old. The first studies on medium entropy alloy can be dated back to the late 1970, beg your pardon, where it was based on undergraduate study. And then another undergraduate thesis was also performed in 1998. Similarly, um, different research were also carried out on high entropy alloys, but the earliest is dated back to 1996, which subsequently leads to 5 publications in the year 2004. This family of alloys have, have attracted different uh, interests from researchers, and they've been given different names. The first one is actually based on the composition of the alloy. Based on composition of the alloy, these alloys have been called complex concentrated alloys, multi-component alloys, as well as multi-principal alloys. Basically, this definition suggests that this family of alloy must be composed of 5 or more principal elements in equimolar ratios or non-equimolar ratios. The requirement for equimolar concentration actually suggests that the principal element must be within the ratio of 35 to 5 atomic percent. However, this definition only consider the composition and not the the elemental configuration of the material. So that leads us to the next definition of this family of materials. The phrase high entropy alloy actually motivates a definition that is based on the magnitude of entropy. Considering this definition, 3 different family or subgroups have been identified based on the level of entropy. The first is low entropy alloys, which are conventional alloy materials. And we have the medium entropy alloy and the high entropy alloy. Actually, the differences is based on the value of the configurational molar entropy in an ideal solid solution. So the value for low entropy alloy actually is below 0.69 gas constant, while the value for the medium entropy is within 0.69 to 1.61 gas constant, while the entropy value for high entropy alloy is actually above 1.61 gas constant. So quickly looking at the classification of these complex of these alloys, because these alloys are very broad, so they will actually group into different categories. Just as we've mentioned, this family of alloys can be called different names. So from now onward in my presentation, I may refer to them as complex concentrated alloys or multi-component alloys or high and medium entropy alloys. So between 2004, when they were first introduced, and between 2004 to 2015, over 500 distinct alloys were identified, and they were classified based on the elemental composition of the parent metals. The group we actually into cis, and these cis families include the 3D transition metals, the refractory metals, the lanthanide transition metals, the complex concentrated brasses and bronze. Then we also have the precious metal complex concentrated alloys, as well as the interstitial compounds. In all of these families, the three largest classification actually include the 3D transition metal, the lanthanide transition metal, as well as the refractory metals. And each of these alloys have different phases and microstructures. Hence, the name for XRD in order to identify these phases. XRD is a useful technique for phase identification for qualitative analysis of intrinsic phases that are present in an alloy. For example, in conventional steel, we have the ferrite, the cementite, and the austenite phases. XRD is also used to determine the crystal structure, whether it be FCC, BCC, or HCP of a material. Okay, and looking at the XRD application for these medium and high entropy alloys. Considering the vast family of the alloy compositions, there's a need for us to be able to identify rapidly the different crystal structures, as well as the different phases that are present in this alloy material. For example, as we'll see in our subsequent slides, when we vary the composition and the proportion of the parent elements in the alloy, there are different macroscopic properties. Therefore, the XRD becomes very relevant in order to identify and optimize this composition to have the best material property. From our lectures, we've seen that the Bragg's law can be used to determine the interplanar spacing in the crystal lattice, and the Chara equation has also been employed to determine grain size, and the Williamson-Hall analysis have also been used for estimating crystal lattice as well as a lattice strain in a given material. Okay, now looking at the phase constituents as well as the microstructure in a typical material, Zhang and his team in 2015 characterized 6 aluminum-based high entropy alloys. Among them is 1 equiatomic and 5 non-equiatomic alloys, as you can see. The XRD of each of these alloys are given in the red view graph, and the major phases have been identified. I'm just going to talk about the first alloy and the XRD pattern of this equiatomic alloy, and that we can find in the first figure, which is figure A. Equiatomic alloy, I mean all of the parent elements have the same equiatomic proportions. Okay, so the diffraction pattern of this equiatomic alloy, which is the first one, reveals a distinct reflection of magnesium tin as well as lithium magnesium tin phases. In addition to this, the aluminum, zinc, and beta tin phases were also identified. And you can see the peak, the intensity, as well as the position as identified in the view graph. So these authors, the Zhang and Stein, in order to identify the macrostructure and the crystal structure of this particular equiatomic alloy, they combined the XRD analysis with SEM and EDS analysis, and they were able to determine the crystal structure of this alloy to be FCC solid solution. Okay, sorry. These alloys that we are actually looking at, just as we mentioned, they are barely 20 years old, but then they've been attracting a lot of research interest and funding because of the very interesting and attractive material properties of this alloy. First, you see that conventional alloy materials like steel and titanium alloys, they have this strength ductility trade-off. High strength corresponds to low ductility, but there are some applications where we have a combined strength and ductility property, and that's where this alloy material becomes very, very interesting. You can see from the table on the slide that even some alloys that has as high as 2000 megapascal as the ultimate tensile strength still have an elongation percentage up to 40 elongation percent. So, and we know that elongation or percentage elongation, which is the strain and fracture intention, is a measure of ductility. And this material property are very intrinsic in these high entropy alloys. Also, these alloy materials have also showed very high thermal resistance. They're able to maintain their strength even at very elevated temperatures, which are very, very unconventional. Materials basically lose their strength properties when they are operating in very high temperatures. But these new high entropy alloys have shown that they're able to maintain their strength. They're able to maintain a balance between strength and ductility. And also, they've also shown increased superplasticity, able to elongate to a very high degree before they can finally yield. They've also exhibited very interesting electrical and magnetic properties. And all of these are possible by varying the elemental composition as well as the proportion of the element present in these alloys. And this has given rise for interesting applications. So the possible direction or possible research in the next couple of years is actually focused on developing high throughput calculations for efficient alloy development. Because these alloys is an emerging material family, there's a need to be able to efficiently and rapidly develop these families of material. And therefore, there is this pursuit for high throughput calculations. Also, there is a need for improved techniques for identifying stable phases at elevated temperatures. In order to rapidly predict the properties of these alloys, there is also relevance for advanced simulation as well as improved analytical techniques. Extensive research in order to understand the type of application that are suitable for a unique family, there is a need for an extensive research, and this research are actually driven by the different industries which have the need for this high entropy alloys. And some of these industries include automotive and the aerospace industries. So as a way of conclusion, we've seen that this material, the high entropy and medium entropy alloys, have a robust combination of material properties that cut across mechanical, magnetic, thermal, and other functional properties. So therefore, they are the best choice of material for lightweight structural application, as well as high strength ductility combination in the material. And these have actually been established due to the improved an existing XRD technique, which have enabled face identification as well as microstructural determination of these materials. And that's the length of my presentation. And there you can see the citations. Thank you, and I hope you enjoyed my presentation.